Hi, welcome to EE16B. My name is Sid,
And I'm Salvan.
and today we'll be covering a midterm problem on how to design a filter.
Just as a disclaimer, this problem is a little bit trickier than what you might expect on the midterm, but we want to go through it just so that you understand how these problems work and how you would be able to do one of these with the current skills that you have.
Cool.
Great. So, question. Design a bandpass filter from omega equal to 10 to the 2 radians per second to omega equal to 10 to the 4 radians per second with a gain of 10 and a roll-off of 20 dB per decade.
Salvan, there's so many terms in this I don't understand. What is a bandpass filter?
It's a good question. So there are there's a lot of lingo and terminology in this. So let's just go through this. Bandpass filter. Bandpass. That means that it lets through, I'm going to put this in quotes, lets through the pass band, which is omega equal to 10 to the 2 to omega equal to 10 to the 4, and stops everything else.
I see.
Okay, so we got that, and then let's see, a gain. The gain is what it is. It's the passband magnitude. So in the passband, we're not just saying that we want it to be flat at 0. We want the gain to actually have some value. So sine waves going in will actually come out larger in the passband and then smaller outside of the passband.
But then what does that mean for the other frequencies? What magnitude would they be?
Well, that's where the roll-off comes in. So the roll-off basically says that outside of passband, the cutoff, outside of the cutoff, the slope drops by 20 dB per decade.
Cool. So it goes continuously until, it just keeps on decreasing
Just keeps on decreasing. So finally, what our graph with the way this has been structured, what it should look like. So your graph would look something like this. It would go up, and this is by 20 dB per decade. It would flatten out during the passband, and then it would come back down at 20 dB per decade.
Wait, Salvan, what are the points at which they stop?
Yeah, that's where the passband part comes in. So this initial point where it starts to level off, this is omega equal to 10 to the 2.
I see.
The second point is omega equal to 10 to the 4. And then the question of where does it start leveling off? Well, that's where this gain part comes in. This says that at 10, is where the passband is going to be.
I see. So we want the gain to be 10 dB.
Yeah, not 10 dB, just 10. So it will be 20 log of
10. Gotcha.
Great. Cool. All right, so step 1 of doing this is to find the transfer function.
Awesome.
And here, we'll just refer to our handy-dandy Bodie plot diagram. So find the transfer function. Okay. So looking at what we had before, right? It went up by some amount, leveled off, and then came back down. We know that this point was at 10, and then these points were at 10 to the 2 and 10 to the 4.
Cool.
And just to get the shape correct, we'll put in the numbers a little bit later.
Okay.
Okay. So, what does this look like to you, Sid?
Well, looking at it, this part looks like, since it goes all the way this way, it kind of looks like this, doesn't it?
Yeah, it does look like it looks like a 0.
Cool.
Just because
so
going up from 0 to infinity, right?
I see. And here we're going to use what the question asks of us, that they're asking for it to go at 20 dB per decade, to figure out what this n is going to be. If I can circle it properly, this n. So we know that the slope goes up at 20 n dB per decade, and since we want to go at 20 dB per decade, this tells us that this n is just 1. So we know the first member of our transfer function is going to be I omega, or j omega. I personally like I, but whatever. Cool. So now, the next thing we're going to try and do is so in Bode plots, we can add things together, right? So what you're going to try and do is find something among these functions to add to this thing, so that at this point, there's no difference. But from here, the increase that comes from this is somewhat cancelled out by a decrease that comes over here. So basically, we want to add something that's sort of like 0 until a certain point, and then decreases down at the same rate as this increases, which is just 20 dB, minus 20 dB per decade. So what does that look like, Simon?
Looks like a simple pole.
Awesome. So we want a simple pole that's 0 over here. This is at 10 to the 2, and then it starts decreasing at 20 dB per decade, so n is simply 1. So let's just add that to our transfer function. So this becomes 1 plus I omega by omega p1. Cool. Simon, what's omega p1?
That's just the first pole frequency, right? So
cool.
10 to the 2.
Exactly. Awesome. Now, so far, by adding these two functions, we have something that looks like this. And then at 10 to the 2, it sort of flattens out and goes on until the end, right? But now, if you can see at this point, we need to start decreasing it again. So we want to add something that does not affect this section, so anything on this side. We don't want anything to be affected there. But from this point onwards, we want a decrease to be added. So, Simon, what does that look like?
Oh, that looks like another simple pole, right?
Exactly. It's this same thing again, but except, what is the cutoff frequency?
The cutoff frequency would be the bigger one, so it would be 10 to the 4.
Exactly. And like before, n is simply equal to 1. So we get something like this, which is what we want. So we add that, to our transfer function. 1 plus I omega by omega p2, where omega p2 is equal to 10 to the 4. Cool.
Great.
So now the next design criteria we need to meet is this 10 right here. We need this gain of 10. But it's not as straightforward as simply multiplying a 10 over here. To figure out what k should be, to figure out what we should multiply, we're going to just put a k over here and then look at the Bode plot of this first, right?
Great.
So
we know that it goes up. It starts off at 0 at 10 to the 0. Mm-hmm. It goes up by 20 dB per decade until 10 to the 2, right? Mm-hmm. So as it's drawn, this should be 40 dB.
Uh-huh.
However, we need this to end up being at 10, which is 20 dB. Mm-hmm. So let's figure out how to deal with this k. Mm-hmm. So basically, it starts off at 10 to the 0. Uh-huh. That's what this 0 at the origin does. And it goes up from this point, which is 0. Uh-huh. And then it goes up by 20 dB per decade to 10 to the 2. Uh-huh. So as it's drawn, so let's write. So this is what our Bode plot we want it to look like, right? Mm-hmm. So what it looks like right now is something like this. Mm-hmm. This is actually at 10 to the 0, this is at 0, mm-hmm. and then by 2 decades later, it has gone up to 40 dB. Mm-hmm. So 40 dB.
Cool.
But we want it to be at 10 or 20 dB.
Cool. So just as a quick clarification, this plot is the Bode plot for this part of the transfer function. We're trying to determine what K is by trying to make this one match this one.
Okay. So now that we got that, we have to bring it down by 20 dB at the passband, right?
Mhm.
So to do that, we would want to set K equal to, well, if we're just adding them together, right? K should be equal to, or rather 20 log K. 20 log K should be equal to minus 20 if we want it to be equal to, if we want it to bring it down by 20 dB.
Cool.
So, bring this over, we get K equal to 10 to the negative 1.
Awesome. Cool. So now, as of the last slide, we've calculated our transfer function to be what you see on the screen right now.
Great. Okay, so Sid, we have a big transfer function, right? But it's pretty hard and kind of unwieldy to deal with if it has so many terms in it. How can we break it down?
Well, looking at it, it kind of looks like it's a product of two filters of some sort. But I'm not sure if we can do that, since there was a homework problem that showed that if you just cascade two filters, there's this weird interdependence between them. Can you explain what's going on?
That's true. So if we have two stages, right? Stage 1, and this is our first filter, and then a stage 2. Then if we just connect them, stage 1 to stage 2, then we'll end up having coupling. We don't want coupling. And that's just because there's a current flowing between them. So how do we prevent that? We put in an op-amp.
Awesome.
So if we put in an op-amp buffer, as we saw in the homework and in some of the notes, then they are effectively decoupled, and we can treat them as separate filters.
So Salvin, how does putting an op-amp help?
Well, an op-amp helps because we know that the current going into the op-amp, IN, is equal to 0. And we also know that the currents track. So V plus is equal to V minus.
The voltages track.
The voltages, sorry. Yeah. V plus is equal to V minus.
Cool.
That means that this input and output voltage are the same. And because there's no current, there can't be any coupling.
Yeah, so it's sort of like we can literally cascade the transfer functions together without thinking twice about it.
Yeah.
Cool.
Okay, so let's start and let's figure out what we want to put into stage 1.
Okay. Does it matter if we put stage 1 or stage 2 first?
It doesn't. We can do either of them in any order. It's just depending on how we want to do it.
Cool.
So, Sid, which one do you want? What should we do first?
Let's do this one first.
Okay. So that one, it looks like just one simple pole, right?
Yeah.
So one simple pole is we know how to deal with that. We know that a low pass filter, an RC low pass filter, or an RL low pass filter, they're both the same. So RC. This produces one simple pole,
Cool.
as we've seen in the notes and all of the discussions.
Really quickly, just write down the transfer function.
Yeah, so let's actually derive it.
Okay.
So moving it into the phasor domain, we have this. V out, V in.
Cool.
So we have a voltage divider here. So we have V out equals V in times 1 over j omega c over R plus 1 over j omega c. So this just becomes multiplying the j omega c's. We have h of omega equals 1 over 1 plus j omega rc.
Awesome. So pattern matching that to what we're trying to get, what does it tell you about RC?
Well, so if we want 1 over RC, if we want the cutoff to equal 10 to the 4th, we know that 1 over RC needs to equal to 10 to the 4th.
Exactly.
So RC is 10 to the negative 4.
Cool.
So off of values I can pick up off the workbench, capacitance, I can get a 1 microfarad. It's one of the larger ones I can pick up. And then to make this balance out, we need an R equal to 10 to the 2
Yeah.
ohms. So 100 ohms.
Awesome. Cool. So now we have the first part of a transfer function done. So I'm going to quickly draw this on the side. Okay, so just for brevity, I have drawn the circuit again in this top corner. Simon, what's the next thing we need to do in order to separate the stages if we were to append it to the circuit I've just drawn?
Well, to append it to the circuit, we need to put in the buffer, right?
Exactly.
So before we put in the next stage, we'd want to have a buffer.
Cool.
Great.
Awesome. Now we're going to start the second stage of the circuit. So, stage 2 of the circuit.
Stage 2.
Stage 2.
Stage 2. All right, so now that we have this part's taken care of,
Cool.
let's look at this other frequency-dependent term, right?
Mm-hmm.
So we could say that, oh, this is just another RC filter, right? This is just another RC low pass. But if we remember what our RC filters look like, we can actually note that this whole thing looks kind of like an RC high pass.
Who
So
would have thought?
an RC high pass looks like this. So just to derive this transfer function again, this is in the phasor domain, this becomes a 1 over j omega c, and this becomes an R, V out,
Cool.
V in. And this is another voltage divider, so we have V out equals V in times R over R plus 1 over j omega c, which means the transfer function h of omega is equal to j omega rc over 1 plus j omega rc.
Cool.
And as promised, we got this j omega, and then we also got this simple pole-in.
Wait, what about the RC part?
Well, that RC is just going to contribute to our last gain term.
Cool.
And then this gain is sort of just a correction at the very end.
I see.
Okay.
Okay, so I'm going to just append this, and we're going to play a quick game of Snake, if that's an appropriate word, and we're going to continue a circuit from here.
Okay. So we got this. We have a C and an R. And then from there, we'll figure out what to do next. So
What are
now,
the values of R and C?
I was just getting to that. So here,
Sassy much?
RC is 1 over RC has to equal to 10 to the 2.
Cool.
So that means that RC product is 10 to the negative 2. All right, so let's just pick,
Let's pick 1 microfarad again.
yeah, why not? 1 microfarad.
Cool.
Let's just get a bunch of bags of those when we're making this circuit. And then to make this 10 to the 2, we need to have an R
Of
equal
10 kilo ohms.
Yeah.
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 10 into 10 to the 3. Cool.
So 10 kilo ohms or 10 to the 4 ohms.
Yeah.
Awesome. So now we know this is another 1 microfarad. This is 10 kilo ohms.
Cool.
And
So what's the RC part that goes into the gain?
well, so we have the RC is equal to 10 to the negative 2, right? So from here, we need to bring this up by a factor of 10, right?
Yeah.
So we're factor of 10 off. So we need to multiply by a factor of 10 our final transfer function.
Cool.
So we need a gain stage that is non-inverting because we don't have a negative sign, and we want it to have a gain of 10.
Okay, cool. Now, the magic of editing, our circuit has increased in length, and the screen has been cleared. Moving on.
Great. So now for stage 3,
Awesome.
which is our final gain stage. So we said that the gain of this stage has to equal to 10 for this final circuit to come together. And then with that, we need, what else? Should it be inverting or non-inverting?
Non-inverting.
Right. And we know that because there's no negative sign here, right? We want h of omega to stay positive. Just like you when studying for this midterm. Stay
Hey.
positive. Okay. So,
I'm kind of jealous I didn't think about that, but okay. You win this time, Salman.
Okay, so non-inverting gauge stage looks like this. You should remember this from your EE16A rules.
Cool.
All right, so this is R1 and R2.
What does R1 and R2 do? What do R1 and R2 have to be?
Well, let's figure that out.
Cool.
So if we just remember what it sort of looks like and don't remember the actual function, let's just derive this really quickly. So this is V minus, this is V plus. So we have V plus and V minus, and we know that we can just perform KCL from here. So we have I1, I2, and I3. Great. So I1 plus I2 plus I3 equals 0.
Why do you care about I1?
Well, we do care about it, but we just know that I1 is equal to 0, so it kind of just drops out.
Cool.
So I2 plus I3 equals 0. I2 is V out minus V minus over R1. Then I3, because of the way I've drawn it, is just negative V minus over R2.
Cool.
Okay, so rearranging terms.
Just as a reminder, V minus is also equal to Vn because of the ideal op-amp rules.
Exactly. So we're just going to put that in.
Cool.
So V out minus V in over R1 plus minus V in over R2 equals 0. Okay, so from here, we can just move this over to this side and say V out over R1 equals V in times 1 over R1 plus 1 over R2. And then finally, let's just draw this in the corner here, or up here. That would probably be better. So V out over V in equals R1 times 1 over R1 plus 1 over R2. So this is just 1 plus R1 over R2.
Cool.
Great. And so we wanted V out over V in to equal 10, right?
Yeah.
So we want it to equal to 10. That means 1 plus R1 over R2 equals 10. And, well, that R1 and R2 just have to be about a ratio of 9. So let's just say R1 is 9 kilo ohms.
Cool.
And R2 is 1 kilo ohm.
Awesome.
Easy enough. And finally, drawing that in. Oops, wrong type of op-amp. Great, so this top one is R1, and this becomes 9 kilo ohms.
Awesome.
And this is 1 kilo ohm.
Cool. And that's our circuit designed.
Great. Good luck on the exam.
Have fun.